Today we will see in detail the angular momentum operators part 3. We are going to see here the total angular momentum operator. And also we are going to see the Clebsch Gordon coefficient, or it is called coupling coefficient. Here by definition the total angular momentum J is equal to L plus S, orbital angular momentum plus spin angular momentum. So I have told you already that J, L and S all comes under Lie group. So properties of all three operators are the same. Uh, Keeping that in mind, we will move further. Let us consider two particle system. J1 and J2 belongs to different particle or different phases. Their component naturally commit. That is commutation of J1 sub J and J sub 2k is equal to 0, where J and k is equal to x, y, z. When J1 squared act on J1 M1, see for particle 1 this is J1, for particle 1 this is M1, J and M. When J1 act on this get vector, you will get J1 into J1 plus 1 multiplied by h cross squared J1 M1. In the case of orbital angular momentum, that is previous two classes, we have seen this eigenvalue is L into L plus 1 h cross square. Same thing I am applying. Instead of L, I am using J, that's all. Similarly, when J2 squared act on J2 M2, remember that here J will act only on J, not on M. That is very important. So when J2 squared act on J2, you will get an eigenvalue of J2 into J2 plus 1 h cross squared J2 M2. This is the get vector. Similarly, the J1Z act on J1 M1. This JZ act only on the M. It will not act on J. So then it will become M1 H cross. In the case of orbital angular momentum also we have seen this is M H cross. Here we are labeling as M1 H cross. Similarly, J2 Z act on the J2 M2, you will get M2 H cross, the get J2 M2. Of course, we are going to rewrite this equation. We will see what will happen if we rewrite this. The four operators that we have seen now, that is J1 squared, J2 squared, J1Z and J2Z form a complete set of commuting operators. So they can thus be jointly diagonized by the same state. So you can do the joint diagonization, denoting the joint eigenstate by J1, J2, M1, M2, that is get J1, J2, M1, M2. We can write them as a direct product of J1, M1, get J1, M1 and J2, M2. That is J1, J2, get J1, J2, M1, M2 can be written as the tensor product of get J1, M1 and J2, M2. The get J1, J2, M1, M2 forms a complete and orthonormal basis using the relation, you know, that this is the get vector outer product. Get vector comes first, then bra vector. So if it is in the reverse order, that is inner product. You know very well. The value of this is 1. You know this value of this is 1, which can be written as from direct product summation over M1, J1 M1. This is also outer product of J1 M1 with J1 M1. Similarly, the outer product of summation over M2, outer product of J2 M2 J2 M2. So on the orthonormal basis, if you take the inner product of this, that is J1 prime J2 prime M1 prime M2 prime with J1 J2 M1 M2, which is equal to Kronecker delta J1 prime J and Kronecker delta J2 prime J2 and Kronecker delta M1 prime M1, and the same thing delta M2 prime M2. Then we will go on further. The problem of adding two angular momenta J1 and J2, that is J equal to J1 plus J2, consists of finding the eigenvalues and eigenvectors of J squared and Jz in terms of the eigenvalue and eigenvectors of J1 squared, J2 squared, J1z and J2z. We know that the commutation of J squared with J1 squared is equal to the commutation of J squared with J2 squared is equal to 0, which we have seen in the case of orbital angular momentum L. So L squared commit with all other component of X. Same thing we are applying because port comes under Lie group. Similarly, J squared, commutation of J squared with Jz is equal to J1 squared with Jz and J2 squared with Jz is equal to 0. Uh, Based on this, we will move further. But in spite of the fact that J squared commit with Jz, the operators J1z and J2z do not commit separately with J squared. Remember that this is a very important point. That is Jz will commit. Of course, this will not commit with J1 Z and J2 Z independently. That is very important. In earlier cases, we assumed that there is no interaction between two particles. Here we are considering the interaction between two particles. So these two will not commit separately, but as a combined effect, it will commit with J squared. That is J squared commit with Z as a combined effect. So J squared is equal to J1 plus J2 whole squared, which can be written as J squared is equal to J1 squared plus J2 squared plus 2 J1 dot J2, which can be written as J1 squared 2 J1x dot J2x plus J1y dot J2y plus J1z dot J2 test Z. Exactly what we have done in the case of operator L operator, that is orbital angular momentum operator. Here J squared will commit with J1 squared, and also J squared will commit with J2 squared. Uh, However, also J squared will commit with Z. But you can see, I want to trust this point. J squared will not commit independently with J1 Z or J2 Z, which is not equal to 0. That is very important point. This is the interaction due because of the interaction between two particles. Since J1 squared, J2 squared, J squared and Jz form a complete set of commuting operators. Remember that here I have not mentioned J1z or J2z like J1 squared and J2 squared, because the as far as Z operator is concerned, it will not commit individually, so it's a combined effect. They can be diagonalized simultaneously by the same state, designating this joint eigenstate by the get J1 J2 J M we have j1 squared. When j1 squared act on this get vector, you will get an eigenvalue of j1 into j1 plus 1 h cross squared and the same get, that is j1, j2, jm. Similarly, j2 squared, it will act only on this j2. So you will get j2 into j2 plus 1 h cross squared, j1, j2, jm. So similarly, when j squared act on it is a combined effect. So it's equal to j into j plus 1 h cross squared, j1, j2, jm. Similarly, jz, this is the combined effect. You keep it in your mind, it's a combined effect. When act on this get, you will get an eigenvalue m h cross with along with this get vector. Since J1 and J2 are usually fixed, we can write the get vector J1, J2, Jm as simply get Jm, where m is equal to m plus m2. J also equal to J1 plus J2. Now the summation over J and summation over m equal to minus J2 plus J, and outer product of Jm is equal to 1 due to completeness property. If you take inner product, that is J prime M prime with Jm, you will get Kronecker delta J prime J delta M prime M. Jm can be written as this outer product of this get vector j1 j2 m1 m2 with j1 j2 m1 m2. You have get jm. See, this is one, the terms which I have shown in inside the bracket is 1. So if you take these two, this outer product will become, when you combine this bra vector and get vector, this is the inner product. So which I have shown here, this is the inner product. This is called Clebsch Gordon coefficient or coupling coefficient. Simply we call it as GG coefficient. GG coefficient. We will see what it is. So, because get Jm can be written as this outer product multiplied by that get vector. This is equal to the Clebsch Gordon coefficient. We will see the detail about it. It is well established that when j squared act on get jm, you will get an eigenvalue of j into j plus 1 h cross squared get jm. Similarly, when jz act on the get vector jm, you will get eigenvalue m h cross with that same get, that is get jm. But now our task is, what will happen if j plus or minus act on this get vector jm? It gives some coefficient with it increases or decreases the mth state by 1. So m plus or minus 1 with some coefficient. We have to find this coefficient. Remember that j plus or minus will act only on this m. Unlike j squared act on this j plus or minus will act on this m. That is very important. Let us label this coefficient as c plus or minus jm with this eigenstate m plus or minus 1. Now our task is to find this coefficient. When j plus act on get jm, we will get expansion coefficient say c plus jm with get vector jm plus 1. This plus represents the rising operator. So you take the complex conjugate and the get vector, that is j plus jm dagger into j plus the get vector act on the get vector j m. So first one you can take c plus j m with the get vector j m plus 1 using this formula dagger whole power dagger. Then next when j plus act on jm, you will get c plus jm, get j in jm plus 1. So now you can have this uh, if you take complex conjugate, this get vector will become bra vector. And if you multiply C plus Jm into C plus Jm, is a complex conjugate and it is C plus Jm. So you will get modulus square of C plus Jm. With this pra vector, get vector will become pra vector. This will be pra vector as it is. You know this inner product of Jm plus 1 with Jm plus 1 is equal to 1. So this will simply become uh, modulus square of modulus square of the C plus Jm. So this is inner product is 1. This inner product is 1. So naturally you will get C plus Jm whole square. So here you can take care of the left hand side. Now if you take complex conjugate of this, then this get vector will become pra vector and j plus will become j minus, and you keep this as it is, that is j plus get jm, which is equal to modulus square of the c plus jm. So the modulus square of the c plus jm is equal to this one, jm j minus j plus jm. From previous class we have seen j plus into j minus is equal to this one. Previous class we have seen this for L minus L plus, which is equal to L square minus H cross Lz minus Lz square. So we have replaced L by J. Now we will reduce it further. Now we got this expression modulus square of C plus Jm is equal to Jm pra Jm j square minus H cross Jz minus Jz square get Jm. When first you take this Jz square act on this get vector, you will get m squared H cross squared. Similarly, when Jz act on this, you will get m H cross. Already there is one H cross. This will become m H cross square. Of course, we have a negative sign both side. Then j squared act on this get jm, you will get an eigenvalue j into j plus 1 H cross square. Since this is a number, you can take out all these things, you will take out. Then only the inner product of jm with jm will become 1. That is inner product of pra jm and get jm is 1. So you will simply get modulus c plus jm squared is equal to j into j plus 1 h cross squared minus m h cross squared minus m squared h cross squared. You know, we have seen when j plus act on get to jm, you will get c plus jm with get vector j m plus 1. Here the modulus square of c plus jm is equal to this one. Then what is c plus jm? Just you take the square root. So when j plus act on get jm, you will get c plus jm. Here I have taken h cross squared outside the square root. So which will become h cross square root of j into j plus 1 minus m into m plus 1 with the get vector j m plus 1. We will move further for the lowering operator. Just now we have seen C sub plus Jm is equal to H cross square root of J into J plus 1 minus M into M plus 1. In similar way, we can find C minus Jm is equal to H cross J into J plus 1 minus M. Here instead of plus you will get minus M minus M1. So when J minus act on get Jm, you will get this coefficient. You will get C sub minus Jm with get vector Jm minus 1. So this expansion coefficient is H cross square root of J into J plus 1 minus M into M minus 1 J M minus 1. So in general we can write J plus or minus get Jm is equal to H cross square root of J into J plus 1 minus M into M plus or minus 1 with get vector J M plus or minus 1. So this is the general expression. For rising operator, we have seen when J plus act on the get Jm, you will get H cross square root of J into J plus 1 minus M into M plus 1 with the get vector J M plus 1. We will see the maximum value for M and minimum value for M. When M equal to 0, sorry, M equal to J, what will happen? Here this will become J, this will become J because M equal to J. Then this will be J into J plus 1 minus J into J plus 1, which will become 0. 0 get to JJ, which is equal to 0. So when J plus rising operator act on the maximum value of n, you will get 0, which we have seen in the case of orbital angular momentum. Similarly, the lower value j minus act on j when m equal to minus j. You can see when m equal to minus j, what will happen? This is minus j, and here m, I am replacing this m also. This m minus j, and this m also minus j. What will happen? This will become h cross square root of j into j plus 1 minus here the minus of minus will become, you take all minus outside, so minus of minus will become plus. So this will become j into j plus 1, which will be again 0. So the upper limit is plus j, I have indicated here, and the lower limit is minus j. So it will reduce us from plus j by the amount h cross, and it will keep on moving and it will become up to minus j. Like in previous case, we have seen the upper limit plus L and lower limit minus L. In this case, we are seeing that upper limit is plus j and lower limit is minus j. This is called touched state. You cannot go above j, and also you cannot go below minus j. Thank you very much for watching my video and supporting me continuously. Thank you very much.